Welcome back to the Mechanics of Solids lecture series. We're working examples solving for beams that are axially loaded. In this example, you were asked to compute the peak compressive stress in the column due to the loading in the frame. It's an L-shaped frame with a distributed load over the beam portion, dimensions as shown, the column cross-section as shown, and I've outlined some steps in the solution process for us. When I see an L-shaped frame like this, what I like to do is make a cut at the beam column joint to find the force and the moment that are transferred to the column. I'll show you what I mean here. If we make a cut and do a free body diagram to the left, to the right of the cut of just the beam portion, we can consider this as a cantilever beam. At the left end, where the joint is, the beam is going to develop a reaction force F and a moment M in the direction that I've drawn. Those forces and moments, in turn, will turn around and be distributed or applied back to the column in the opposite direction. So this is the force and moment acting in the column. And hopefully it's fairly evident that the force and the moment acting in the column are constant throughout the column. Okay? The maximum compressive stress is going to occur on this interior side of the column. That's the compression side of the member. Anywhere along that section should develop the same stress in compression. So let's go ahead and proceed. We can evaluate the force as being equal to the total load, the W of which is 10 kips per feet times the length of 10 feet gives us 100 kips. The moment, we can use my shortcut WL squared over 2 equal to 10 kips per feet times 10 squared divided by 2, or 500 kip feet. The second step is to define a coordinate system. To be consistent with what we're used to, I like to define the x-axis along the member. I like to have bending about the z-axis, which would be the axis coming out toward us. So I'm going to draw the y-axis in this direction. Okay, so that as usual I can apply sigma x equals my over I. The third step, compute the section properties. Section properties that I need are the area equal to 14 times 10, or 140 inches squared, and the moment of inertia I equal to 10 times 14 cubed over 12. 14 is the dimension in the y direction, so that's the one I want to cube since we're bending about z. And that result is 2286.7 inches to the fourth. Okay, finally, last step to compute the stresses. I'll use my equation, sigma x equals F over A minus M C over I, or y over I. I'm not going to worry about the sign here too much, because remember we said that on this side of the member both of the terms are going to be compressive. So what I really want here is just to compute the values and then make both of the terms negative. And I'm reasoning out the sign by inspection. Okay? Sigma x equals F over A, 100 kips divided by 140 inches squared, plus the moment, 500 kip feet, times a conversion factor of 12 inches per feet, times c value, the distance to the right side of the column is half of its depth, or 7 inches, and then divided by the moment of inertia, 2286.7 inches to the fourth. Remember, the whole thing is going to be negative, and this computes to a result of negative 19.08 KSI, which is a compressive stress, and that's my answer. And that completes this video series.